When we discuss polarity, you're going to also hear it called a dipole moment. And a dipole moment basically just means if there is an overall dipole, which means an unequal distribution of charges, that means the molecule is polar. So we can utilize these partial negative, partial positive symbols when we're discussing polarity to kind of help us look at an overall, like almost tug of war situation. So here we have a molecule of water, H2O, and a lot of times on the water molecule or any molecule, they don't show the lone pairs, but you have to keep in mind there's a lone pair. So what's going on here is this is an unequal distribution of charge. We call that a polar covalent bond, meaning there are electrons being shared between the O and the H, but it is being held closer or kind of hogged by the oxygen. So right here is an unequal distribution, and then on this side is the same thing, an unequal polar covalent bond. Now, because they are both heading towards the oxygen, we show this dipole moment symbol towards the O, meaning most of the electronegative charge from the electrons are being pushed towards one side of the molecule. And that creates an overall polar molecule. So we say an overall polar molecule has an overall dipole moment, which means it has an unequal distribution of charge when you look at the entire molecule. Now, a nonpolar molecule can have dipole moments, which means polar bonds. All right, but they actually cancel themselves out overall, and therefore the whole molecule would be nonpolar. So let's look at some examples here. So a polar molecule has a dipole moment of a number greater than 0. We will not be calculating this in any sort of way. Sometimes they're just giving you a value. If it has an actual value, then it just tells you that it's a polar molecule, meaning there is some unequal distribution of electrons in the entire molecule. And we usually put an arrow towards the direction of the atom that has the electrons closer to them. And so you can see here on the first example, we have a polar bond. When we have an H and a Cl, Cl gets the partial negative sign and H gets the partial positive, meaning although they're sharing, which is a covalent bond, the shared electrons are closer to the Cl. And you can again below see that in the H2O molecule, same thing here, because there is lone pairs on the oxygen and these unequal pooling of the H and the O, overall there is a dipole moment, meaning it's polar. And you can again see that at this third molecule here. Keep in mind that this molecule has a lone pair. Now, what I want you to get from this is that you need to see a full Lewis structure to really figure out if something is polar or nonpolar. Sometimes by looking at these pictures, they don't show you the full picture, basically. They're not showing you any lone pairs on the center atoms, and that can create a very big dipole if there is a lone pair. So step one, when trying to figure out polarity of a molecule, draw the Lewis structure. Now, here are some examples of nonpolar on the right side. We do not have an overall arrow being shown, but basically they're just being pulled equally in between the molecules that they're being shared between. So for example, here is CO2. And so although this might be a polar bond, a polar covalent, and this is a polar covalent bond, because they're being pulled out in opposite directions, that makes our dipole moment equal to 0. So a nonpolar molecule can have polar bonds, but overall they cancel each other out and there is no overall dipole. Same thing happening here with the CCl4. No lone pairs on that C, and there are 4 bonds being pulled, shared bonds being pulled towards the outside molecules, and therefore since they're pulling equally, that is a nonpolar bond. So basically an overview of this idea is a polar bond has some sort of separation of charge, usually that being the electrons are being held closer to one atom than the other. Because of that, we therefore have a dipole moment, which is given by this little U letter, and it's a number that is above 0. So we can draw and represent the charge separation by using either two things. We can draw the arrow towards the more electronegative atom. Remember, the most electronegative atom on the periodic table is fluorine. So if an atom is closer to fluorine, it has a greater pool of electrons. And we can also use this partial negative, partial positive symbol. They draw it a lot better than I do, to indicate that difference in charge. So as I've kind of hinted earlier, how to determine if a molecule is polar, you're going to first draw the Lewis structure. A lot of times this also relates VSEPR, molecular geometry and shape. You do not need to draw the 3D structure to exactly figure out polarity. It does help. And then you're going to look at symmetry. Okay. Now I do have a little bit of a hint here. If there is a lone pair, one or more lone pairs on the center atom, it is automatically polar. So it's just something to kind of keep in mind. If there is a lone pair on the center atom, one or more, it is polar. Polar is a lot more of a common, molecule type. So again, here is the distribution of dipoles. Again, I told you the CO2, even though these are both polar bonds here, they are canceling each other out. So it's kind of like tug of war. You have two of the same strength pulling on this center atom. Therefore, there is no overall pull. So therefore, that is non-polar. And in H2O, it is definitely an unequal pooling. More of the electrical charge is in the vicinity of the O and not near the H's. They do not cancel out, therefore the molecule is polar. Now we're going to use polarity to determine how things bond with each other, in relation to boiling points, melting points, freezing points, things like that, if things are soluble or not in water. So we are going to be using polarity to tell us a lot of things in the future. So it's a good skill to be able to look at a molecule and pick if it is polar or not pretty quickly. So let's practice here. So determine if the molecule is polar or non-polar. I'm going to kind of talk you through my thinking. So to save us some time, I went ahead and drew our Lewis structures. You're welcome to go ahead and try those just to make sure that you know how to do that. And the reason why, you cannot just look at a molecule and say, hey, this is polar. And the reason why is because you need to look at the center atom in relation to everything around it. So if I were to look at GeF4, yes, there are 4 polar bonds. This is a polar bond, this is polar, this is polar, this is polar, right? But overall, it is being pulled towards the more electronegative atom in the same 4 directions outwards. Therefore, this molecule 100% is nonpolar because everything's canceling out. Now, let me just give you another scenario example. Let's pretend that this was a Cl. That would make this molecule polar because it would be pulling differently in one direction than it would in the others. So it has to be the same atom, the exact same atom pulling on all the sides for it to be nonpolar. Okay? Sometimes that's a pretty common question, so I always like to tell people ahead of time. So because this is all fluorines pulling on the center atom, that is a nonpolar molecule. Now, SF2, again, you'd have to draw it so that you can see the 2 sets of lone pairs located on the sulfur atom. And the way you want to think about this is, yes, this is being pulled on either side by fluorine, but this is also being pulled on either side on the top and the bottom by these lone pairs. They are not pulling the same as fluorine pulls. And although it is equal on the sides and the top and the bottom, it is not equal overall. It has to be 100% equal, just like this GeF4 was, for it to be nonpolar. So because there is at least 1 lone pair on the center atom, this is a polar molecule overall. Now this last one, ASF3, again, you had to draw that so you could see this lone pair. Seeing the lone pair on the center atom really is just a very clear identifier that this molecule is polar. Okay? Hopefully that helps you with polarity.